If you are somehow connected to science and mathematics, you must have seen this question paper from IIT BHU. Those students who have attempted this question, it's okay, but those who haven't can still raise an issue on this question because there is a fault in this question. This question is from the movie scene when Captain America picks up Thor's hammers and throw it towards Thanos. Now, when he has to throw the hammer, he has to apply some force on it, and this is what is being asked in this question. That our Cap throws the hammer at Thanos with his might. The total load applied here is 16 kilopounds. Consider the hammerhead to have a circular cross section with diameter 7/8 inches. Find the stress when this load is applied to throw the hammer. What is the stress at the handle of the hammer which has a diameter of 5/8 inches? Check figure. The actual answer to this question is not what you were supposed to answer in the exam hall. Let me first tell you the solution that students were expected to answer in the exam hall. This is a simple stress and strain problem. You have given the force applied, you have given the cross-sectional area. Don't go for these values, these have been framed for the next part of the question, in which the hammerhead would return to its original shape after deformation, but the handle would undergo plastic deformation. And if you draw the hammer with the given dimensions, it would look something like this, which is kind of misleading. Because when I first saw this question, I expected the cylindrical shape to be in this direction. It's a paper from IIT BHU, it cannot be that simple. And it must be in this direction to make the calculation much harder. But it's not. And anyone with 11th standard physics can easily solve this question. It's a simple stress and strain problem. You have given the force applied, you have given the cross-sectional area. Axial tensile stress is given by force upon area. Just put the values and get the answer. Although not in SI units, but this was what you were expected to answer in the exam hall. But this is wrong. Question is not, but the solution is, and every single student that have done this is wrong. Where is the problem? Just pause the video and think about it. Okay. All the problem starts with this formula. This force in this formula is not the force that we apply on the object. Otherwise, it would be just the definition of pressure. It is the internal force induced within the object in response to oppose the force that we have applied on the object. The atoms in a solid are arranged in lattice and held together by interatomic bonds like covalent or ionic bonds. When we apply an external force, we are actually disturbing these atoms arranged into lattice, either push or pull. And as we try to deform the object, these bonds resist the motion, creating internal forces. This resistance per unit area is what we call stress. It's a material's natural tendency to fight back and to return to its original force. And this is the force that we put in the formula. But how do we know that this force is equal to the applied force? Because usually we directly put the value of force given to us in the question. This is the whole point of this video, which has been misunderstood while framing this question. When force is applied to throw the hammer, it's just one side of the object that is subjected to the force, while the other end of the object is free to move. The force which is being applied to induce the stress is used by the object to get acceleration. When the formula stress equals force by area is written from the definition of stress, the object is under a net force 0. And for demonstrations, it's fixed at one end and other end is subjected to the force. By Newton's third law of motion, there is an equal and opposite force applied by the wall at the fixed end. And the object is under a balanced force from both the sides, which causes deformation of the object and inducing stress within the object. But in the case of a hammer thrown, there is nothing that is holding back this hammer, except its inertia of rest. Consider this. I have this pen in my hand, and I am going to apply some force on it from both the sides. That force will cause some stress and strain inside this marker, which I can calculate using the formula of F by A. Now, as I increase the force, there will be a threshold force that will generate so much stress and strain inside this object that this object will reach to its rupture point and breaks apart. Under ideal case, this force is going to the same for the same cylindrical object of same material and same cross-sectional area. I can write down this force, and whenever I am going to apply the same force, it will break apart. Now, my question to you is, apply the same force, but the point is, you have to apply the force from only one direction. Only one side of the object will be subjected to the force. What do you think? Will it gonna break apart? The answer is a clear, big, obvious, bold no. But the formula stress equals force upon area is still saying that you are applying the same force, the cross-sectional area is same, the stress induced will be the same, and corresponding strain will be the same. But this object is not going to break apart. What is happening now? This is exactly what is happening when we are throwing a hammer. The whole point of saying is that the formula stress equals force upon area works only if the object is under a balanced force. That is, the force is applied from both the ends, not just one end of the object is subjected to the force. But obviously, there will be some stress induced within the object. How will we calculate that? With all the information that I have provided you till now, you cannot directly calculate the stress of the object as a whole using this formula. For the exact setup of the problem, there are certain things that have to be assumed. First of all, we have to understand what will cause the stress to be induced within the object. Forget the hammer, let's just solve it for a cylindrical object. Equations will complicate you. I have the slinky with me, tied to this string and tied to this weight. Now, as this weight is released, it will pull that slinky and apply a constant force on it. Although a very delicate representation of stress and strain, but here we go. The moment the force is applied, there is a quick deformation at the face exposed to the force. And as the slinky accelerates further, this stress wave travels along the slinky with the reduced amount of strain as it gains velocity. But if you look closely, the amount of strain is reduced along the length of the slinky. Maximum at this region and almost no strain in the end. But why is that happening? Keep in mind, this is not an exact replica of the problem. This is not a rigid body, but the hammer is. But one important observation we can take from here is that the stress induced is not constant throughout the length of the object, being maximum at the face exposed to the force and almost no stress on the opposite end. Let's do the math. Consider a uniform cylindrical rod AB with all the standard assumptions. Let its length be L and cross-sectional area be A with a uniform mass density rho. Let a constant force F is being applied at the end B and A is free to move. Due to this force, this rod will accelerate, given by the Newton's second law, that is force by mass. And the mass is just density times volume, which is density times area times length. We need to calculate the force that is being applied at any particular slice of the cylinder. Consider a point that is at a distance of x units from A. Because it too is accelerating with the same acceleration, the force required at this point will be just enough to pull the mass of this part of the cylinder. Let's say mx, and let the force be fx. Again, Newton's second law. Fx is mx times acceleration, which is density times area times x. Equate the acceleration from both these equations. Density and area cancels out, and we are left with force Fx is F times x by length, and the stress will be internal force by cross-sectional area, that is A. And if you put the bounds for verification at x equals L, the value is just F by A, which is same as the standard formula of stress. And at x equals 0, there is no stress and corresponding strain. For all the standard assumptions, this formula will calculate the stress of an accelerating rod. But still, there are certain things that are very different from the actual dynamics of an hammer throw. When force is applied to throw a hammer, for a small period of time, the free end have no information of force being applied. The stress wave moves from one end to another end at a speed of root over E by rho, where E is the Young's modulus and rho is the density of the object. As the object sets into a constant acceleration, the stress is governed by this equation. But when we throw something, we have to eventually let it go. Like a lot of other things, we have to let it go. There is no more connection between you and the hammer. Means that you cannot apply more horizontal force on the object, and the object sets into a constant motion, and the internal forces start to dominate, and the object gets back into its relaxed state. Those who want to read it in detail, I have created a report using Gemini, link in description. And for a disclaimer, let me tell you something. Last time I formally studied mechanics of solids was 6 years ago when I was in 11th standard. And when I saw this question, as an obvious fact, I know that my 11th standard knowledge is not going to be enough to solve this problem. And I went on to NAPTEL. But as the lectures continued and I covered more than half of the syllabus, I realized that things have started to deviate from what's being asked in the question, because it's a midterm exam and I have already covered more than half of the syllabus. And that was the point I realized that something is missing. Then I went on to ask the students who attempted this question and even mailed the professor. And yes, everything that I was thinking wrong was right.